For this video, we'll talk about periodicity. And for this part of video, we have two learning outcomes. We will talk about the variation in atomic radii. We'll talk about two variations. First one is going down a group. So we are going to talk about what happened to the atomic radii when you go down a group of the periodic table. And also we are going to look into going across a period. The second learning outcome of this video is we are going to compare the atomic radius of the element and also its ion. Means we are going to compare the atomic radius of the neutral atom with its cation, and also we are going to look into the neutral atom versus its anion. So we are going to look into the size between them. Atomic radii. We have two cases over here, like I said. The first one is going down a group. So generally, when we're going down a group, the atomic radii increases. It means that we are going to start with a smaller size at the top and ended up at a bigger size at the bottom of the group. The second variation that we're going to look into is going across a period. Going across a period, the atomic radii decreases. It means moving from the left to the right of the periodic table. The atomic size was starting on the left slightly bigger. Going across the period, it will end up a bit smaller. So we are going to look into why this variation happened. And also we are going to look into the factors affecting both of them. We have two factors affecting atomic radii. The first one, effective nuclear charge, or we call SES. That is the symbol of effective nuclear charge. The second is the shielding effect. An effective nuclear charge will be used when we are going across a period, while shielding effect will be used when we are going down a group. If your element is in the same period, then we are going to discuss about effective nuclear charge. If the element is in the same group, then we are going to use shielding effect. First and foremost, we are going to look into effective nuclear charge. So, effective nuclear charge or SES will be used, like I said, when they are in the same period. And what are actually effective nuclear charge? Effective nuclear charge is the net positive charge that experienced by the valence electron from the nucleus. What is meant by this sentence? That is your standard atomic model where you have your nucleus in the center. In the nucleus, you have the presence of proton. And you know that proton will be your positive charge. And you have your electron in the energy level. And the electron will be holding negative charge. So between the negative charge and the positive charge in the nucleus, you will have something called force of attraction. The force of attraction will happen because of the positive charge in the nucleus and the negative charge of the electron. This force of attraction is what we call effective nuclear charge experienced by the valence electron. In the other words, if the effective nuclear charge is very strong, what happened to the valence electron? The valence electron will be pulled closely to the nucleus. And if the valence electron is now close to the nucleus, alright, what happened to the size? The size of the atom will become smaller. Right? Agree? And we are going to look into how can the effective nuclear charge can be strong. How can the atomic radii become smaller when it goes across a period? We have a formula to calculate effective nuclear charge, where the formula is Z minus S. So what is Z and what is S? Z is actually the number of proton. S is the number of inner electron. What is inner electron? All electron other than valence electron. So when you minus the valence electron, the remaining is what we call inner electron. For example, if I have sodium 11, your electronic configuration will be something like this. And we agree on your 3s1 is your valence electron. If your 3s1 is your valence electron, then your 1s2, 2s2, 2p6 is what we call your inner shell, and your inner electron will be 10 because you have 2 plus 2 plus 6. And the effective nuclear charge of sodium will be the number of proton, which is 11, minus the number of inner electron, which is 10, and the effective nuclear charge of sodium will be positive 1. And the higher the effective nuclear charge, the stronger the attraction. And we know that effective nuclear charge will be applied when we are going across a period. So let's look into one example of period 3. Period 3 is moving from sodium all the way to your argon. The first element that I have is sodium, and the sodium electronic configuration as given. We have learned on how to determine the valence electron in the previous video. So if you don't understand why this is the valence electron, please watch the video of 6.1. That is your valence electron of your sodium. Therefore, the remaining electron over here will be your inner electron. So your inner electron having 2 plus 2 plus 6. So your inner electron is 10. And the number of shell is 3. The number of shell is 3 because it's a period 3. When it's a period 3, you know that you're going to have 3 shell. Your principal quantum number will be 3. Your n equals to 3. So the number of shell will definitely be 3. How about your effective nuclear charge? Your effective nuclear charge will be the proton minus inner electron. So the proton over here is 11. So you have your 11 minus your inner electron 10. So your effective nuclear charge for your sodium will be positive 1. The second element in your period 3 is your magnesium, where the proton number increases to 12. So your proton number now is 12, where the electronic configuration as given, and your 3s2 is your valence electron. Since your 3s2 is your valence electron, so the remaining electron will be your inner electron. And your inner electron is how many? Your inner electron is 10 because you have 2 plus 2 plus 6. So your inner electron is 10. The number of shell remain 3 because again it's still in the period 3. And you can see from the highest n, the highest n is n equals to 3. How about the effective nuclear charge? Effective nuclear charge will be again the proton minus inner electron, Z minus S. The proton of magnesium is 12. You have 12 proton. And then your inner electron remain 10. So the effective nuclear charge increases to positive 2. So we can see a trend of proton number increases across the period and effective nuclear charge increases across the period. So let's check for another tool. Next, we have aluminium. Aluminium proton number again increases to 13. And you can see over here, your 3s2, 3p1 is your valence electron, as we have learned previously. The remaining electron at the back there is what we call inner electron. And again, if you realize the inner electron remain the same. The inner electron remain 10, the number of shell remain 3. So both of these so far remain constant when you go across the period. And how about the effective nuclear charge? Effective nuclear charge again, proton minus inner electron. Proton is 13 minus inner electron 10. effective nuclear charge increases to positive 3. Last but not least, one more element in the period tree, silicon. So this is your electronic configuration and this is your inner electron. Why? Because this is what we call valence electron. And the number of shell again remain 3. The highest principal quantum number, the highest n, is 3. And also, it proven that all of them are in period 3. The inner electron also remain 10. Inner electron is not changing when you go across a period. But the effective nuclear charge increases. So what would be the effective nuclear charge of silicon? Silicon proton is 14. So you have 14 minus 10 equals to positive 4. So you can see over here, the effective nuclear charge when you go across a period, effective nuclear charge increases. The inner electron remain the same. The number of shell remain the same. Proton number increases. So when you go across period 3, the proton number increases. Therefore, the effective nuclear charge increases. And when the proton number and the effective nuclear charge increases, the force of attraction increases. When the force of attraction increases, the atomic size will decrease because the valence electron will be pulled closer to the nucleus, therefore the size becomes smaller. And also, when you go across a period, the number of shell remain the same. And when you go across the period, the inner electron also remain the same. They are not changing. The only thing that change is the proton number. So the conclusion of effective nuclear charge when going across a period, it doesn't matter whether it's a period 2 or whether it's a period 3. When you go across a period, the proton number in the nucleus will increase, but the number of inner electron remain constant. And therefore, the force of attraction from the nucleus to the valence electron increases. When the force of attraction increases, the effective nuclear charge increases. As a result, the valence electron will be pulled closer to the nucleus or drawn closer to the nucleus. Therefore, atomic radii will decrease when you move across the period. So always remember, when you move across the period, we will use the effective nuclear charge to discuss. And when we talk about effective nuclear charge, proton number is the main thing. And when you go across the period, proton number increases. That's why the force of attraction from the nucleus to the valence electron increases. Okay, simple, very, very simple. Next, we'll talk about shielding effect. What is actually shielding effect? Bear that in mind, shielding effect will be used when we are talking about elements in the same group or when it's going down a group. Shielding effect will be extremely high when the inner shell is higher. So I can show you what I mean by this. So that is my nucleus, where in my nucleus, you know that you have the presence of your proton. So in the proton, you know that it's a positive charge. So your nucleus is a positive charge. And then you have your first shell, where you have your n equals to 1. And then you have your n equals to 2. So you have your electron out there. And you know that your electron is a negative charge over here. And your nucleus attraction will be from the nucleus all the way to the valence electron. And that is your force of attraction. And right now, your force of attraction is shielded by one inner shell. Before your force of attraction from the nucleus reach until the valence electron, your force of attraction from the nucleus need to go through n equals to 1. Then only it will reach n equals to 2. So from the nucleus, you need to reach n equals to 1. Then only it can reach n equals to 2. So that is your shielding effect. Okay? And let's compare with this. Again, that is your nucleus. So in your nucleus, you have your proton and the positive charge. So you have your inner electron, and that is your outermost electron, your valence electron. So your nucleus attraction will be all the way from the nucleus to the valence electron. That is your force of attraction. And by looking at this, you have your n equals to 1, you have your n equals to 2, you have your n equals to 3. And your force of attraction right now is shielded by 2 inner shell. Alright? So a simple word for shielded is like it's blocked by 2 inner shell. Your force of attraction need to go through first energy level, then only it can pull the second energy level electron, then only it can reach the valence electron. So which one do you think will have a bigger atomic radii? This one will definitely have a bigger atomic radii. Why? Because the number of inner shell is higher. When the number of inner shell is higher, the shielding effect is higher. When the shielding effect is higher, the force of attraction will be weaker. When the force of attraction is weaker, the valence electron will be far away from the nucleus. When the valence electron is far away from the nucleus, the atomic radii increases. Okay? So bear that in mind, when the shielding effect increases due to the higher number of inner shell, and the atomic radii will also be bigger. Simple? Let's look into some example. When I go down group 15, I have nitrogen, phosphorus, arsenic, and so on. Let's look into the electronic configuration of nitrogen. Electronic configuration of nitrogen as given. And from here, we know that 2s2, 2p3 is your valence electron. If this is your valence electron, 1s2 will be the inner electron. So I have 2 inner electron over here. And the number of shell is 2. So you can see n equals to 1, n equals to 2. So number of shell is 2. Effective nuclear charge over here will be 7 minus 2. And the effective nuclear charge is positive 5. Because you have 7 proton minus 2 inner electron. So the effective nuclear charge positive 5. Another element in the group 15, you have your phosphorus, where the valence electron over here is your 3s2, 3p3. That is your valence electron. Therefore, the remaining will be your inner electron. And how many inner electron we are having? We will have 10 inner electron over here. And the number of shell is 3. The number of shell increases. In the other words, nitrogen will have 2 shell. Phosphorus will have 3 shell. Alright? And the effective nuclear charge will be phosphorus 15 proton number minus 10 inner electron, and the effective nuclear charge remain positive 5. And last but not least, another element in the same group, I have arsenic, and in arsenic, the valence electron is 4s2, 4p3. That is your valence electron. Therefore, the remaining electron back here will be the inner electron. And let's count how many inner electron arsenic having. Arsenic having 28 inner electron. The number of shell increases to 4, which means arsenic will having 4 energy level, 4 shell. Okay, and the effective nuclear charge of arsenic proton number 33. So you have your 33 minus inner electron 28, and the effective nuclear charge of arsenic remain positive 5. So you know that right now, going down a group, the effective nuclear charge remain the same. Therefore, when you go down a group, you cannot discuss by using effective nuclear charge because the effective nuclear charge is the same. What else is the same? You realize that the valence electron is 5. The valence electron is 5 every single element. So when you go down the group, other than effective nuclear charge is the same, the number of valence electron also the same. But what is changing? When you go down a group, you realize that the number of shell increases. Can you see? When you go down the group, the number of shell increases from 2 to 3 to 4. When the number of shell increases, what happened to the shielding effect? This is your nucleus. Your nucleus need to reach to the valence electron. So you need to go through one shell and then it will reach the valence electron. For phosphorus, that is my nucleus, I need to reach 1, 2, and then I reach my valence electron. For the arsenic, I need to reach 1, 2, 3, and then only I reach my valence electron. So when the number of shell increase, the shielding effect also increases. And when the shielding effect increase, what happened to the force of attraction? The force of attraction obviously decreases. When the force of attraction decreases, the valence electron will be very far away from the nucleus and the atomic radii will increase. That's why when you go down the group, the size of the atom become bigger. And the conclusion of it is, when you go down a group, the number of shell increases. When the number of shell increases, the number of inner electron also increases. When the number of inner electron increases, the shielding effect increases. When the shielding effect increases, the force of attraction from the nucleus to the valence electron become weaker, a lot weaker. And when it's weaker, the valence electron will be moved further away from the nucleus. When the valence electron is very far away from the nucleus, the atomic radii will become bigger when you go down a group. Okay, and all that is because of shielding effect, and the shielding effect will be greatly affected by the number of shell. And the number of shell will only change when you go down a group. That's why for the shielding effect, you only use when you are going down the group. Make sense? Simple? Very simple concept. Okay? And the next learning objective is, we are going to compare the size of the neutral atom and also its cation. So, everybody know that when neutral atom want to become a cation, we are going to remove electron. Then we can become a positive charged ion. Let's use an example, a very simple example, sodium. Sodium 11, when it's neutral, the electronic configuration is this, 3s1. And when sodium become cation, sodium will be positive 1, but the proton number remain the same. The only thing that changing is we remove 1 electron to become 1s2, 2s2, 2p, 6. And like I said just now, the number of proton for both of the neutral atom and also cation will remain unchanged. The number of proton will be the same. But what happened to the number of electron? Number of electron in neutral atom is 11 because it's neutral. So number of proton equals to number of electron. But in the cation, the number of electron will be only 10. Number of electron decreases in the cation. Okay? And since the number of electron decreases in the cation, but the proton remain the same, therefore, the force of attraction in the cation will be stronger. Why is that stronger in the cation? Because the proton number in the nucleus is the same. You have 11 positive in the nucleus and you're only pulling 10 electrons. Over here, you have 11 positive in the nucleus, but you are pulling also 11 electrons. So which one will have a stronger force of attraction? 11 pull 11 and 11 pull 10. Obviously, this one, the force of attraction is stronger. When the force of attraction is stronger over here, so which one do you think that have a smaller size? Obviously, the cation will be smaller in size compared to your neutral atom. Because in your neutral atom, the force of attraction is weaker. So your neutral atom will be bigger and your cation will be smaller. That is your neutral atom. That is your cation. So the size of the neutral atom is bigger than the cation. As a conclusion, all neutral atoms will be bigger in size compared to their own cation, no matter what is the charge of the cation. Next, and last but not least, let's look into neutral atom comparing with anion. So you know that neutral atom means there is no charge, anion means there is a negative charge. And from neutral atom, once you become your anion, we are going to accept electron. Means what happened to the number of electron. So let's use a very simple example. I have fluorine 9. The fluorine 9 over here is 1s2, 2s2, 2p5. And what happened when fluorine become anion? Fluorine become negative 1. But the proton number remain the same. Only changing is the electron. 1 electron is added into the 2p5 to become 2p6. And fluorine changed from neutral to become F- ion. And as we agreed previously, the number of proton for both of them will remain the same. Number of proton is the same right now. But what is changing? Number of electron. Number of electron in the neutral atom will be 9 because it's a neutral, so proton equals to electron. In the anion, the number of electron increases to 10. So the number of electron increases. In the anion, because you are accepting electron to form negative charge ion. So what happens when the number of electron increases? One thing that we call mutual repulsion increases. What is actually mutual repulsion? Mutual repulsion can also be called as electron repulsion. Why electron will have repulsion? Because all electron is in negative charge. So when all electron is sitting together, the negative charge will repel each other. So in the anion, the mutual repulsion increases because we added in electron. So when the electron added, the electron and the electron in the ion will be repelling each other. So when the mutual repulsion increases, therefore the electron cloud will spread out. When the electron cloud is spread out, it will be far from nucleus. So when the electron cloud spread out and far from the nucleus, the electron is now very far from the nucleus. What happened to the force of attraction? Force of attraction from the nucleus to the valence electron will decrease. When the force of attraction decreased, what happened to the size of anion? The anion right now will be bigger compared to your neutral atom. That is your fluorine neutral, that will be your fluorine minus. Your anion will be bigger than the neutral atom. And all that because of the electron increases, and therefore the mutual repulsion increases. And when the mutual repulsion increases, electron will be moving far from the nucleus, and therefore the force of attraction from the nucleus to the valence electron decreases. As a result, the size of the anion will be bigger than the neutral atom of the same species. And that's it for this part 1 video. And I hope you understand this theory. They are very simple. We only talk about force of attraction from the beginning till the end. We want to know the force of attraction from the nucleus to the valence electron is stronger or weaker. So think about that. And if you like this video, don't forget to give me a like and subscribe to my channel for more informative video. Thank you for watching. I'll see you in the next video.